Welcome back. In this video, we are going to solve problem 1-22 that is taken from chapter number 1, Stress. And the book name is Mechanics of Material by R.C. Hibbeler. So statement is the metal stud punch is subjected to force of 120 Newton on the handle. Determine the magnitude of reactive force at pin A and in short link BC. Also determine the internal resultant loading acting on the cross section passing through handle arm at D. So you can see 120 Newton load is applied on handle, and we have to find the reaction force at the pin as well as in link BC. And then at point D we have to find the internal loading. So let's start with the solution. So first step is that if you remove this link at point if you remove this link BC, so there will be a reaction force at point B. Let this force is FBC, and if you remove this pin support at point A, so you will be having a reaction force horizontal which is AX, and there will be a vertical reaction force which is represented as AY. Now you can find the this reaction force by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So from here you can see that this angle is 60 degree. There this angle is 60 degree, so this will be 30 degree. And if I draw a line like this, so this angle will be also 30 degree. Now FBC have two component. One is this X component and other is this Y component. Clear? So we can also represent this component like this. This will be FBC Y component, and this will be FBC X component. Okay, so about point A, the one moment is produced due to this 120 Newton load, and perpendicular distance is 500 millimeter, and that is 0.5 meter, and this will produce clockwise rotation, so it will be negative. So I will write it first 120 into 500, and that is negative. The second moment is produced due to this component of FBCX component there, and perpendicular distance is, you can see, that is 50 millimeter, and this is producing clockwise movement, so it will be positive. The vertical component is passing through A, it is not producing movement, so I will write plus FBC into X multiplied by 50 is equal to 0. So minus 120 into 500, and FBCX is equal to FBC into cos of 30 degree. FBC into cos of 30 degree multiplied by 50 is equal to 0. So from here you will get this FBC will be equal to 1385.6 Newton, or you can say 138. We will get, if you round it, so 1.39 kilo Newton. So this is the value of FBC. So in first part we have find out the magnitude of force in short link BC, which is FBC. Now we will move toward finding AX and AY. For that we will apply equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see vertically we have this one force AY. Clear? The second one is this force FBC, and we will take the vertical component of this. So let me first define the vertical component. If I draw a vertical line over here, so you can see this angle is 30 degree. How? This line is perpendicular. Okay, you can see that the angle between these two lines is 30 degree, and this line is perpendicular to this. Clear? And this vertical line is perpendicular to this line. So the angle between these two will be also 30 degree. So now this 120 will have two components. One is this component and other one is this component. So this component is equal to 120 into sine of 30 degree, and this component will be 120 into cos of 30 degree. So now you can see this is the vertical force, this is the vertical force, and this is the vertical force, and their sum must be equal to 0. So I will write minus FBC. FBC is 1385.6 plus AY, which is upward, minus this component, which is 120 into cos of 30 degree. Their sum must be equal to 0. So from here, when you calculate it, you will get AY will be equal to 1489.56 Newton, or you can see 1.5 kilo Newton. So this is the vertical component of reaction force at point A. Now we'll find this AX by using another equation of equilibrium, that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So you can see we have one force which is AX and other one is this component. Their sum must be equal to 0. So I will write minus AX plus 120 into sine of 30 is degree is equal to 0. So from here you will get AX will be equal to 60 Newton. So this is the answer of our first part, in which we have been asked to determine the magnitude of reactive force at pin A and short link BC. Now the resultant of this horizontal and vertical force can be obtained by using Pythagoras theorem, and let this is reaction force A or FA. So we can find this FA reactive force at pin A will be equal to AX square plus AY square under the root. So put the value, AX is 60 square plus AY is 1489.56 square under the root. So here when you calculate, it will be 1491 Newton. Or you can see that force at point A will be equal to 1.49 kilo Newton. Okay. Now in second part, we have been asked to determine the internal loading acting on cross section passing through handle arm at D. So for that we will cut the beam over here at D, and we will draw the free body diagram. So free body diagram will be like this one. So this is the handle portion, okay, and then you have let me correct it, and then at point D, so D is this one, D is this one. So when you cut it, you will get it like this. Okay, so here you can see you have 120 Newton force that is acting perpendicular to this surface, 120 Newton. And at point D, when you cut it, you will be having a shear force, which is, this is point D, which is equal to VD. You will be having a normal force, which is equal to ND, and you will be having a moment, which is equal to MD. So how you will get the distance between this and the point of application of 120 load is given as 300 millimeter. Now you can see we have to change the coordinates. So what we will take is that we will take this x coordinate in this direction, because here we have normal load and the shear force will be in this direction. This is y dash. So we will apply equation of equilibrium. That first equation of equilibrium is that sum of all forces along x dash must be equal to 0, and force in this direction is taken as positive. So you can see one force is this one, which is nd, and the second force, which is this one, their sum must be equal to 0. So I will write nd minus 120 is equal to 0. So nd will be equal to 120 Newton. Now we'll find the second force, that is Vd. So for that we'll apply equation of equilibrium, that sum of all forces along y dash direction must be equal to 0, and force in this direction is taken as positive. So you can see along this we have one force is Vd, and there is no other force, so it means that only Vd, so Vd is equal to 0. Okay, we will find this moment md by using equation of equilibrium, that sum of all moments about point D is equal to 0, and taking the counterclockwise moment as positive. So about this point D, one moment is this md, which is counterclockwise, so it will be positive. The second moment will be at point D, will be due to this 120, and perpendicular distance is this one, which in meter is 0.3, and this is producing clockwise, so it will be negative. So I will write md minus 120 into perpendicular distance is 0.3 meter is equal to 0. So when you calculate it, you will get moment about point D comes out to be 36 Newton into meter. So these are nd, vd and md are internal loading at point D, and that is the answer of our second part. And this was all about this problem 1-22. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then I will request them to subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 1-23, that is taken from chapter number 1, Stress, and book name is Mechanics of Material by R.C. Hibbeler. Statement is solve problem 1-22 for resultant internal loading acting on cross-section passing through the handle arm at E and cross-section of short link BC. So we will use the same data for problem 1-22, which we have solved in our previous video, and now we'll solve this problem 1-23. So you can see 120 Newton load is applied on the handle. So we have to find the internal loading at cross section E and in link BC. So let's start with the solutions. First step is that if you remove this link at point B, so you will replace it with a reaction force, and this reaction force, that link applied at point B is equal to FBC. And when you remove this support, pin support at point A, so you will be having reaction, horizontal reaction force AX, as well as vertical reaction force AY. So we will find only FBC, because we will then work on the right portion, right hand side of the problem, and we will find is this FBC. So for FBC, we will apply equation of equilibrium, that is sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So you can see the load is applied like this, and this FBC is vertical. So what we will do is that we will convert this load FBC into its component. One is along this direction and other one is along this direction. So you can see that this angle is 60, so this angle will be 30, and if I extend this line, so these are the vertical angle, so this is 30 degree. Now this FBC will have two component. One is along this direction and other is along this direction. Clear? Or you can say this component will pass through point A. So this is FBC sine of 30 degree and this component is FBC cos of 30 degree. So this is the same FBC sine of 30 degree because these two reactions forces must pass through point B. Okay. Now sum of all moment about point A must be equal to 0. So first load is 120 and perpendicular distance is this 500 and this is producing clockwise, so it will be negative. So I will write it first 120 into 500, that is clockwise, so it will be negative. The second moment is due to this load FBC into cos of 30 and perpendicular distance is this 50 and this is producing counterclockwise movement, so it will be positive. So I will write plus FBC into cos of 30 degree into 50 millimeter is equal to 0. So from here when you calculate this, FBC will be equal to 120 into 500 divided by 50 into cos of 30 degree and you will get this FBC will be equal to 1385.6 Newton, or you can say 1.3856 kilo Newton. So this is FC, reaction force in member BC. Okay, now you can see if this is the member BC, when you cut it over here, so you can see the load that is taken by this member BC is FBC. So when you cut it, you will be having a shear force, you will be having a normal force. Clear? And let's say this shear force is V, this normal force is N, and you will be having a moment M. Okay, so we'll find this internal resultant loading in member or in short link BC. So for that I will apply equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see this FBC, which is this one, 1385.6 minus this normal force is equal to 0. So normal force in member in short link BC will be equal to 1385.6 Newton, and that is 1.3856 kilo Newton. So this is the normal force in member BC. Now for shear force we will apply equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So you can see in this direction only force is shear force, there is no other force, so it means that V is equal to 0. Now we'll find moment and let this take point is 0.1. So sum of all moment about 0.1 is equal to 0, taking the counterclockwise movement as positive. So again at 0.1 this force is passing, this force is passing, and there is only external movement over here. So it means that movement will be also equal to 0. And these are the answers for a resultant internal loading in short link BC. Now we will move toward this part and we will cut this handle at point E and we will draw the free body diagram. So let me draw it first. This is the handle portion. Okay, So at this point we have a load of 120 Newton, 120 Newton. This is point E. So when you cut it, so you will be having a normal force perpendicular to this face, and this is equal to NE. You will be having a shear force along the surface of this is VE, and you will be having a moment which is ME. Okay, the distance between this E and this line is, you can check the above as well, this is 100 millimeter, and from this till this point this distance is 300 millimeter. Now what we will do is that we will apply equation of equilibrium, that sum of all forces along x dash is equal to 0. So what is x dash? So you can see this, let this distance is taken as x dash and this coordinate is taken as y dash. We will resolve these forces into this x dash and y dash. So first equation of equilibrium is this one, and force taken in this direction is taken as positive. So you can see the NE which is acting in this direction is only force, there is no other force, so it means that NE will be equal to 0. So I will write NE is equal to 0. Now we will apply another equation of equilibrium, that is sum of all forces along y direction must be equal to 0, y dash direction must be equal to 0, and force in this direction is taken as positive. So from here you can see one force along this y dash direction is this VE, and the second force is this 120. So this is taken as positive and this will be taken as negative. Their sum must be equal to 0. So VE minus 120 Newton is equal to 0. So from here VE is equal to 120 Newton. And the last thing is moment about point E. So we'll apply equation of equilibrium, that sum of all moments about point E is equal to 0, taking the counterclockwise movement as positive. So about point E, one movement is this one which is counterclockwise, so it will be positive, and the second movement that is produced due to this 120 and perpendicular distance is 400 millimeter, and this is producing clockwise, so it will be negative, and their sum must be equal to 0. So I will write ME minus 120 into perpendicular distance 400, which in term of meter is 0.4, is equal to 0. So from here you will get movement about point E comes out to be 48 Newton into meter. So this NE, VE and ME is the resultant internal loadings at point E, which is the answer of our this part. So that was all about this problem 1-22, in which we have been asked to find out the internal loading in member BC, which we have find out this normal force, shear force and moment, and internal loading at cross section at point E, which is NE is equal to 0, shear force is 120 Newton and moment is 48 Newton into meter. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 1-17, that is taken from chapter number 1, stress, and the book name is Mechanics of Material by R.C. Hibbeler. So statement of problem is that determine the resultant internal loading acting on section AA and section BB. Each section passes through the center line at point C. So you can see this is the beam having a pin support at point A and a roller support at point B. And at this point we have a load of 5 kilonewton. So you have to find the internal loading in section AA. So for that you have to cut the beam at this and you have to find the internal loading, and then you have to cut the beam at section BB and you have to find the loading at point C. Both these sections are passing through center point C. So let's start with the solution. So first step is that if you remove this roller support at point B, so you will be having a reaction force. Let this force is NB, clear. And if you remove this pin support at point A, so you will be having a reaction force of having AY, as well as there is horizontal reaction force which is AX. So we can find them by using equation of equilibrium. So let's find the equation of equilibrium. We will find NB because we will cut the beam at this section and we will take this regions for finding internal loading. So for that I will apply equation of equilibrium, that sum of all moments about point A is equal to 0 and taking the counterclockwise movement as positive. So what we will do is that you can see that if this is the horizontal, if I draw horizontal line, so this angle is 45 between this line and horizontal line, so this angle will be also 45 degrees. So it means that NB will have two component, one is this one and other one is this one. So this component will be NB into sine of 45 and this component will be NB into cos of 45 degree. So the first moment that is produced about point A is this 5 kilonewton force, and the perpendicular distance between these 2 points are 4.5 meter, and it is producing clockwise movement, so it will be negative. So I will write first 5 into 4.5 and that is negative. The second moment is produced due to this vertical component that is acting at this, and perpendicular distance is 6, and this is producing counterclockwise movement, so it will be positive. These two forces are not producing any movement because it is passing through point, as well as this horizontal component is also not producing because it is passing through this point. So I will write the vertical component which is NB into sine of 45 degree multiply by the perpendicular distance is 6, and this is producing counterclockwise movement, so it will be positive. So when you solve this you will get this NB will be equal to 5.303 kilonewton. Now you have this reaction force NB. You can also find AY, AX, but we do not need. So what we will do is that we will internal loading for section AA, for section AA. So section AA is this one. So if you cut the beam here and draw the free body diagram, so let me draw it first. So this is the beam, clear. This is your section AA. So when you cut the beam, so you will be having a normal force which will be equal to NAA. You will be having a shear force which is VAA, and you will be having a moment which will be MAA. Okay, this is your point B where you have a load NB which is 5.303 kilonewton, and that makes an angle of 45 degree with here. At this point we have a 5 kilonewton load that is acting perpendicular. This is the load, clear, 5 kilonewton. The distance between this end till this end, this is 1.5 meter, and from section this is also 1.5 meter. Now we'll find this internal loading by using equation of equilibrium. So what we will do is that if you have, this is your x dash direction and this is your y dash direction. Okay, we will remove the arrow signs. So we'll apply equation of equilibrium is that sum of all forces along x dash direction must be equal to 0 and force in this direction is taken as positive. So x dash is this direction, clear? So you can see in this direction one force is NAA and the other force which will be in this direction will be its horizontal component, which will be equal to 5.303 into cos of 45 degree. Their sum must be equal to 0. So I will write it. NAA is in our positive direction. So NAA plus this its vertical component and this is its horizontal component. So this is N B into cos of 45 degree. So I will write plus NB is 5.303 into cos of 45 degree is equal to 0. So from here we will get NAA will be equal to minus 3.75 kilo Newton. Now this value is negative. It means that we have taken the NA direction in this is wrong. So N should be in this direction. Okay. But the value of this force is 3.75. Now we'll find VAA by using equation of equilibrium is that sum of all forces along y dash direction must be equal to 0 and force in this direction is taken as positive. So you can see this VAA is in this positive direction and the other load this will be also in this positive direction. And the third load which is 5 Newton is in negative direction. Their sum must be equal to 0. So I will write VAA plus this vertical component which is this one and this one is 5.303 into sine of 45 degree minus this load which is downward is equal to 0. So again when you calculate it you will get VAA dash is equal to 1.25 kilo Newton. So since this value is positive it means that our assumed direction of VAA in this direction is correct. In this direction is correct. Okay. Now we'll find this moment by using equation of equilibrium and that equation of equilibrium is that sum of all moments about point C is equal to 0 taking the counterclockwise moment as positive. So you can see this is a point C where we have cut this section. So what we will do is that if you can see that these forces are not producing any moment because this is passing through. So we have the reaction moment which is MAA that is negative and because it is clockwise. So I will write minus MAA. The second moment that is produced due to this load 5 into perpendicular distance is 1.5. This is also clockwise, so it will be negative. So I will write minus 5 into 1.5. And the third moment that is produced due to this vertical component about C and this will produce counterclockwise moment, so it will be positive. So this vertical component which is 5.303, I will write 5.303 into sine of 45 and perpendicular distance is now 3. So I will write plus 5.303 into sine of 45 degree into perpendicular distance is 3. Their sum must be equal to 0. So when you solve this you will get the value of moments that will come out to be 3.75 kilo Newton into meter. Since this value is positive it means that our assumed direction of movement which is in clockwise is correct. So this is the internal loading for section AA. Now we will find internal loading for section BB. So for BB you have to cut it along this and you have to draw the free body diagram. So let me draw it. This is the beam This is the beam, and let me draw it again because this is not a rectangular. So this is the beam, and this is the section BB. Here you have N, that is 5.303 kilonewton, making 45 degree with this. Here at we have N, that is 5 kilonewton. This distance was 1.5. This distance was 1.5 meter, and this distance is now not 1.5. And when you cut it, you will be having a reaction force, which is NBB. You will be having a shear force along this vertical shear force. Sorry, this surface is vertical, not it's not. This surface is, let me take like this, because section BB is this one. This is your section BB. Okay, BB. So you will be having a shear force in this direction, that this is BB, clear, and you will be having a moment MBB. So we'll find this by using equation of equilibrium. So you can see that here this BB is vertical and it's making angle of 45 degree. Also this is 45 degree. So if this beam is, this line is 45, so it means that this angle is 45 degree. So if I draw a horizontal line over here, this is 45 degree, this total is 90 degree, and the sum of this angle plus this must be equal to 180 degree. So it means that this angle is also 45 degrees. So you can see that you will have two component of this 5 kilonewton. One is this and the second one is this. Clear? This component will be equal to 5 into sine of 45 degree, and this component will be 5 into cos of 45 degrees, this component. Now apply equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So you can see about x-axis we have one load is this one, the second one is this NBB, and third one is this one. Their sum must be equal to 0. So this is positive, this is negative, and this is also negative. So I will write 5 into cos of 45 degree minus 5.303 minus NBB is equal to 0. So you will get NBB will be equal to 1.768 kilonewton, and this value is negative also, so it means that our assumed direction is wrong. NBB should be in this direction. Now we will find this VBB. For that we will apply equilibrium equation, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So along vertical we have VBB, we have this vertical component which is 5 into sine of 45, and the other one is this no vertical component, because we have taken horizontal component is like this one. So what will be the VBB? VBB and minus this 5 kilonewton into sine of 45, minus 5 into sine of 45 degree is equal to 0. So it means that VBB will comes out to be 3.54 kilonewton. And the last thing is that moment MBB. So for that we will apply equation of equilibrium, that sum of all moment about point C is equal to 0, and taking the counterclockwise moment as positive. So this was your point C. So about point C, the moment is external moment, which is MBB, that is clockwise. So I will write minus MBB. The other moment that is produced due to this 5 kilonewton load, and perpendicular distance between this 5 and C is 1.5, and this is also producing clockwise, so it will be negative. So I will write minus 5 into 1.5, and the third moment that is produced is the vertical component of this force, which is F3.303 into sine of 45, and perpendicular distance is 3, and this is also producing counterclockwise movement, so it will be positive. So I will write plus 5.303 into sine of 45 degree into perpendicular distance 3 is equal to 0. So when you calculate it, you will get MBB will be equal to 3.75 kilonewton into meter, which is the moment at section BB. So these NBB, VBB and NBB is internal loading at section BB. And that was all about this problem 1-17. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also leave your comment about this video. Thank you so much. Welcome back. Problem 1-18. So this problem is taken from chapter number 1, that is stress, and the book name is Mechanics of Material by R.C. Hibbeler. And the statement of the problem is the bolt shank is subjected to tension of 80 pounds. Determine the resultant internal loading acting on the cross section at point C. So you can see we have been given that the bolt is subjected to 80 pounds in tension. So we have to find the internal loading at point C, at cross section at point C. So this will be normal force, there will be a shear force VC, and we have moments. All these are internal loading. So let's start with the solution. So first step is that if you cut this at point C and draw the free body diagram. So first I will draw the free body diagram. It will be like this. Okay, then we have like this. So this is your point C, where you have a normal force when you cut it, clear, and this normal force will be NC. There will be a shear force which will be VC, and there will be a moment, reaction moment, MC. We have been given that in this shank of the bolt we have a tension. So the force that is exerted by this bolt on this portion will be in this direction, clear, and this will be 80 pounds. So this force will be 80 pounds. Also, from point C till this, the radius is given as 6. So this distance from this till the mid of this, we have this distance is 6 inch. Now we will apply equation of equilibrium in order to find this MC, NC and VC. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So you can see only horizontal force is NC. So I will write this is in plus direction, so NC, and the second force that is 80 pounds in positive direction. Their sum must be equal to 0. So from here you will get NC is equal to minus 80 pound. So our answer is negative. It means that we have assumed this direction NC is toward right hand side, which is negative. So I will write, so our assumed direction is wrong and NC should be towards left hand side. Okay, but the magnitude of NC is 80 pound. Now we'll find VC by using another equation of equilibrium, and that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So here you can see only the vertical force is VC, which is acting downward, and there is no other vertical force. So I will write minus VC is equal to 0. It means that VC, there is no vertical shear force acting on this at this point. Now the third load is that we will use the third equation of equilibrium is that sum of all moment about point C is equal to 0, taking the counterclockwise moment as positive. So about point C, these force NC and VC are not producing any moment because these are passing through this point. We have a reaction moment which is MC, that is counterclockwise. So I will write MC, and the moment that is produced due to this 80 pound force into perpendicular distance at about point C is 6. So 8 into 6, and this is also producing counterclockwise movement, so it will be positive. So I will write plus 80 into 6 is equal to 0. So from here you will get this MC will be equal to minus 480, and the unit will be in pounds into inch. So this is the reaction moment, and we can see that this moment comes out to be negative. So it means that our assume direction of MC is wrong, and it should be in clockwise direction. To keep equilibrium. To keep it in equilibrium. And this was all about this problem 1-18. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1-21. This problem is taken from chapter number 1, that is stress, and the book name is Mechanics of Material by R.C. Hibbeler. So statement of problem is the forced steel clamp exert a force of 900 Newton on the wooden block. Determine the resultant internal loading acting on section AA passing through point A. So you can see this is a forged steel clamp and that exert 900 pounds on this wooden block. This is wooden block. You have to find the resultant internal loading at section AA passing through point A. So it means at point A you have to find the normal force, shear force and moment. So let's start with the solution. So first step is that when you cut this clamp at section AA and draw the free body diagram. So first of all I will draw the free body diagram. So this is the clamp portion. So here you can see you have like this curve form. So let's draw it like this. Okay. This is section AA. Clear? This is section AA. And this section AA makes angle of 30 degree with this horizontal. This is your point A. Clear? Now when you cut it, so you will be having a normal force acting on this surface which is equal to NAA. Clear? You will be having a shear force on this face which will be equal to VAA, and you will be having a moment which will be MAA. Now you can see that this clamp exert force of 900 Newton on this wooden block. As a result, the wooden block will exert 900 Newton force in upward direction on this clamp. Also, the distance between this point A and this application of this force is 200 millimeter. So this distance is 200 millimeter. Now we will take this x-axis, this will be as x dash axis, and this will be y dash axis, because your this normal force and shear force exert along this axis. So we'll find the internal loading by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x dash direction must be equal to 0, and force in this direction is taken as positive. So you can see this is the 900 Newton force that act perpendicular to this surface. So if I extend this line, if I draw a line that is at 30 degree with the horizontal, and this 900 will have two components. One is this component which is equal to, we will talk, and the second one is this component. Clear? So what will be this angle? This angle. So you can see this is 30, this will be 60 degree. So this will be also 30 degree. So this component will be equal to 900 into cos of 30 degree, and this component will be 900 into sine of 30 degree. So we will apply equation of equilibrium. So first equation of equilibrium is sum of all forces along x direction must be equal to 0. So one force along x dash direction is this one, which is VAA dash, and this is toward positive. We have taken this direction as positive, this direction. So this will be negative. And the second force is this one, which is 900 into sine of 30. So their sum must be equal to 0. So I will write minus VAA plus 900 into sine of 30 will be equal to 0. So from here you will get VAA, which is the shear force, and this will be equal to 450 Newton. Now we will find this NAA, and we will use the equation of equilibrium is that sum of all forces along y dash direction must be equal to 0, and force in this direction is taken as positive. So you can see this force NAA is in positive direction. Clear? And this component is in negative direction as per our understanding, or assumed direction. So their sum must be equal to 0. So I will write NAA minus 900 into cos of 30 degree is equal to 0. So from here NAA will be equal to 900 into cos of 30 degree, and that will be equal to 779 Newton. So you have NAA as well. We will find this moment MAA. So we will apply equation of equilibrium that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, one moment is MA, which is clockwise, so it will be negative. The second moment about point A will be this load 900 into perpendicular distance is 200 millimeter, and this is producing counterclockwise, it will be positive. So I will write minus MAA plus 900 into 200 millimeter, and 200 millimeter in meter is 0.2 meter. So from here you will get MAA will be equal to 900 into 0.2, which is equal to 180, and unit will be Newton into meter. So all these are the internal loading at point A, and that is the answer of our this question. And that was all about this problem 1-21. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Also leave your comment about this video. Thank you very much. Welcome back. Problem 1-45. This problem is taken from chapter number 1, that is stress, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the pedestal has a triangular cross section as shown. If it is subjective to compressive force of 500 pound, specify x and y coordinate for the location of point PXY, where the load must be applied on the cross section so that the average normal stress is uniform. Compute the stress and sketch its distribution acting on the cross section at location removed from point of load of application. So you can see this is a triangular pedestrian where this point P having coordinate x, y, and a load of 500 pound is applied, that is compressive. So you have to find the location of this x and y coordinate where this load is applied, and then you have to find the stress and its distribution. So let's start with the solution. So you know that this is a triangle, clear, and this is its x-axis and this is its y-axis, that is shown over here. So for triangle, we have to find its centroid, and for finding the centroid we have this P is centroid, so Px comma y, its coordinate will be equal to x1 plus x2 plus x3 divided by 3. That will give its x coordinate, and for y this y1 y2 plus y3 divided by 3. So you can see this is its x-axis and this is its y-axis. Let this point is your point number A, where x coordinate is equal to 0 and y coordinate is 0. Let your this point is point B, where x coordinate is 0 and y coordinate is 3 plus 6, which is equal to 9. And let this point is your point number D, where x coordinate is equal to 12. You can see here x coordinate is 12 and y coordinate is 3. On y axis this is 3. On y axis this distance is 3. So this will be 12 comma 3. Now you can find its x coordinate. So x will be equal to x1 plus x2 plus x3 divided by 3. So x1, you can see this is x1 which is 0, plus this is x2 which is also 0, plus x3 which is 12. So 12 divided by 3 is equal to 4. So x coordinate will be 4 inch. Now y coordinate will be equal to y1 plus y2 plus y3 divided by 3. So y1 is 0, you can see y2 is 9 and y3 is 3. So 0 plus 9 plus 3 divided by 3, which is again 12 by 3, and we will get 4 inch. So location of point P, which is the centroid, and its component coordinate x comma y is 4 inch and 4 inch. So this is the answer of our first part. Now in second part, we have been asked to find the stress. So that is equal to this. We know that stress is equal to load per unit area. So load is given as 500, that is compressive there. So 500 divided by area of triangle. So area of triangle is equal to 1 over 2 into its base. Base, you can see this is the base, which is 9, and its altitude, which is 12. So 1 over 2, 9 multiplied by 12. And when you calculate it, you will get the stress is equal to 9.26 psi. So this is the answer of our second part. Now in third part, we have been asked to find the distribution sketch. We have to sketch this stress acting on the cross section at a location removed from this point of application. So its stress distribution will be like this. As the load is compressive, so this will be like, the load will be like this. Similarly, on this face and on this face, the stress will be downward. So this is the load or distribution of stress along its cross section away from the point of load of application. And that was all about this problem 4-1-45. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you. Welcome back. Problem 1-41. So this problem is taken from chapter number 1, that is stress or internal loading, and the book name is Mechanics of Material by R.C. Hibbeler. So statement is, if average normal stress in each of 20 millimeter diameter bar is not allowed to exceed 150 megapascal, determine the maximum force P that can be applied to joint C. So you can see this is a truss A, B, C, and each of this bar of the diameter is 20 millimeter, and allowable stress should not exceed 150 megapascal. So you have to find this maximum load P that can be applied to joint C. So average normal stress in each of the bar should not exceed 150 megapascal, that is 150 into 10 raised to the power 6 Pascal, and diameter of each rod AB, BC and CA is 20 millimeter, that is 0.020 millimeter, and we have to find the maximum force P at joint C. So let's start with the solution. So from this truss, you can see it is a right angle triangle. So we have to find this angle theta. Clear? So we know that AC is given as 1.5 meter and AB is given as 2 meter. So we'll find this AC. So AC is not known. So by using Pythagoras theorem, we know that AC square is equal to, sorry, AC, this is BC, not AC. So BC square is equal to AC square plus AB square. So you can just put the value, AC is 1.5 square plus AB is 2 square, and we take the square root on both sides, will give you length of BC. So from here you will get this BC will be equal to 2.5 meter. Now you have this BC. So what we will do is that we will take joint C, take joint C as C, and we will analyze it by method of joint. So you can see due to this load P, it will cause the compression in AB. As a result, the load applied by this BC on point C will be like this. And similarly, due to this load P, it will move, this AC will move toward this side, causing extension or tension. As a result, the load applied by AC at joint C will be this one. So let me draw this joint C. So this is a point C where you have a load of P that is acting in this direction, and this is the load BC at this point. This is load BC, and this load BC will be in this direction. Let this load is FBC, and at point C the load due to FAC or AC will be like this. Let this is FAC. Here this FBC will make an angle theta. So we'll find this theta, and we know that tangent of theta is equal to here this perpendicular, which is AC, divided by this hypotenuse, which is BC. So I will write AC over BC. The length of AC is 1.5, length of BC is 2.5. So from here we will get theta is equal to tangent inverse 1.5 divided by 2.5. And when you calculate it, you will get this theta will be equal to 36.86 degree. Now you have this theta, so you can see that we will apply equation of equilibrium for finding this FAB and FAC. So first equation of equilibrium is that sum of all forces in the x direction must be equal to 0, and force in this direction is taken as positive. So horizontally there is a force P applied, and the second one is the horizontal component of FBC, which is FBCX component, and that will be equal to FBC into cos of theta. Clear? So I will write plus P minus FBC cos theta, that is equal to 0. So P is there, P minus FBC, we are interested to find of FBC. So FBC will be equal to P divided by cos of theta. And when you put the value of theta, P divided by cos of 36.86, so when you calculate it, 1 divided by cos of theta will give you 1.25. So FBC is equal to 1.25 times P. Now you have this FBC. We'll find this FAC by using another equation of equilibrium, that is sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see one force that is acting vertically is this minus FAC because it is downward, and another one is this vertical component of FBC, which is equal to FBC sine of theta. So I will write minus FAC plus FBC into sine of theta is equal to 0. So we have to find FAC. So FAC will be equal to FBC sine of theta, and sine of theta is 36.86 degree. Okay. So we know now FBC, which is 1.25 times P. So FAC is equal to 1.25 times P multiplied by sine of 36.86 degree, and you will get FAC is equal to 0.75 times P. So I will write FAC is equal to 0.75 times P. Now you can see that initially I have told you that this member is in compression FAB, clear, and this member will be in tension. So we will write it over here. I will choose another color. This is in FBC is in compression, so I will write C, and FABAC is in tension. Okay. Now we'll move toward another page. We will find this FAB. So for that we will take this joint B and we will apply method of joint. Okay. So take point B and apply method of joint. Okay, so here at point B you can see that you have a reaction force that is due to this roller support at point B. This is By. Due to this member BC, there is a force which is in this direction FBC, and this makes angle theta with horizontal, and there is a load due to this member FAB. So the load will be like this one. So we will draw it over here. So this is point B. This is your point B. Here you have a load due to reaction load which is By. Clear? On horizontally there is FAB which is in this direction, and load due to FBC is like this, and this makes an angle theta. This is FBC. So we will find this FA by using equation of equilibrium, and that is sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So horizontally we have this FAB in this direction which is negative, and the other one is this horizontal component of this, and this horizontal component is FBC into cos of theta. Their sum must be equal to 0. So I will write minus FAB plus FBC into cos of theta is equal to 0. We are interested to find out FAB, so FAB is equal to FBC into cos of theta. FBC, which we have calculated, is 1.25 P. So 1.25 times P, and cos theta is 36.86. So when you calculate it, you will get this FAB is equal to P. And again you can see that this load is on joint B is like this. So as a result, this load will be the load in stress in member AB is in tension. Okay, so I will write this as tension T. Now you have FBC which was 1.25 times P. You have FAC which is 0.75 times P, and FAB is equal to P. So we have to find the maximum P at joint C. So for maximum loading, average normal, let me write it, average normal stress. Since the cross-sectional area and allowable normal stress of each bar are the same, member BC having maximum normal force. You can see that this member is a maximum 1.25 times P. So maximum normal force is the critical member. So critical member. So we will find this P based on this average normal stress. We know that average normal stress allowable is equal to FBC, because this is the maximum divided by area. These two values are same, so we will get FBC is equal to FBC is equal to allowable into area, and area for circular rod or bar is equal to pi by 4 d square, and d is 20 millimeter or 0.02 meter square. So you will get area is 0.3142 into 10 raised to power minus 3 square meter. Now this FBC is equal to 1.25 into P is equal to allowable stress. Allowable stress is 150 into 10 raised to power 6 psi. So 150 into 10 raised to power 6, and area is 0.3142 into 10 raised to power minus 3. And when you calculate it, you will get P will be equal to 150 into 10 raised to power 6 into 0.3142 into 10 raised to power minus 3 divided by 1.25. And you will get this load P will be equal to 37.699 Newton, or this P is equal to 37.7 kilo Newton, which is the answer of this question. And that was all about this problem 1-41. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1-40. So this problem is taken from chapter number 1, that is stress, and book name is Mechanics of Material by R.C. Hibbeler. Statement is determine the average normal stress in each of 20 millimeter diameter of bar of the truss set P is equal to 40 kilonewton. So you can see this is the truss that is made of bar ABC, AB and AC that has diameter of 20 millimeter, and P is equal to 40 kilonewton. So you have to determine the average shear stress in each bar AB, AC and AB. So let's start with the solution. So first step is that we will find internal loadings. How you will find internal loading? So we will use method of section. I will write it. Method of joints in order to find the stress or force in each member. So we will take point C as we will take joint C, and we will find the forces. Let this is joint C, where there is a load of P that is equal to 40 kilonewton is applied, and at point C you can see there is a load of BC, and this BC will be in this direction. Clear? This I will represent it as FBC, and at point C we have a load due to in member AC that will be downward. It is represented as FAC. Now from this figure you can see this length is 1.5 and this is 2. So if I draw a triangle, right angle triangle over here in order to show the ratio of its length, so this side is 1.5, this is 2, so definitely this hypotenuse will be equal to 2.5. Now we'll apply equation of equilibrium at point C. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So you can see one force is this one and the second force is its horizontal component, which is in this direction, and this will be equal to FBC x. This component will be equal to FBC x component. So I will write its two component. One is in this direction and the second one will be in this direction. This component will be equal to FBC x component and this component will be FBC y component. So for x component, I will write 40 kilonewton in positive direction. So 40 minus FBC x component will be equal to 0. Now if this is making an angle of theta, so cos of theta will be equal to base, which is 2, divided by hypotenuse, which is 2.5, and this FBC x will be equal to FBC into cos of theta. So I will write from here 40 minus FBC into cos of theta will be equal to 0. So 40 minus FBC is not known. So FBC and cos of theta is 2 divided by 2.5. So 2 divided by 2.5 is equal to 0. So from here you will get this FBC will be equal to 50 kilo Newton and the value is positive. So it means that the direction which we have taken is correct and this is in compression. This force exerted by member on point C is in this direction. As a result, the force in member is in compression. Now we'll find the second force by using equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So one force which is downward is minus FAC and other force is plus FCY. FBC y component is equal to 0. So minus FAC and FBCY is equal to FBC into sine of theta is equal to 0. And sine theta, you can see that here sine theta is equal to perpendicular, which is 1.5 divided by hypotenuse, which is 2.5. So if you put the value, so minus FAC plus FBC, which is equal to 50. So I will put the value 50 into sine of theta and that is 1.5 divided by 2.5 is equal to 0. So you will get FAC will be equal to 30 kilonewton. The value is positive, so it means that the force exerted by this member at point C is in compression. So as per Newton third law, this force will be in tension. The force exerted by this member on this at point C will be this. So as per Newton law, the force in this member will be tensile one. So it will be in tension. Now we will find another equation of equilibrium by using method of joint, and we will take joint B. So if you take joint B and you want to find, this is point B, this is point B and this is the load FBC. Now at point B it should be in downward direction because the force exerted by member BC at joint B will be compression, so FBC. And at point B you have a roller support, so you'll be having reaction force which is BY. And there is a horizontal force of member AB which will be in this direction, FAB. Again we will draw the same rectangle triangle for this. So this is 1.5, this is 2, and this is 2 point, hypotenuse is 2.5. Now apply the equation of equilibrium. The sum of all forces along x direction must be equal to 0, and this force in this direction is taken as positive. So you can see along the x-axis one force is of this component will be this one, and the other one is this one. This sum should be equal to 0. Now you can see that this has two component. One is this and other one is this one. So this, let this is theta. So we will you can see that it's, if we take sine of theta, so sine of theta will be equal to 2 divided by 2.5 for this angle. So here this component will be equal to FAB is in negative direction, so FAB plus this component FBC into sine of theta will be equal to 0. So from here you will get this FAB is equal to FBC into sine of theta. And when you put the value, you will get this FAB will be equal to FBC. FBC is 50 into sine of theta is 2 divided by 2.5. So you will get FAB will be equal to 40 kilonewton. So this is the force. Now as a result, the force in this member will be in tension. Clear? So I will write it. This is tension. Now we'll find the average shearing stress. So average normal stress. Average normal stress, we know that this average normal stress is equal to force per unit area. Area will be obtained by using this formula. Pi by 4 d square. Diameter of each member is given as 20 millimeter. So you can just put pi by 4 into 20 millimeter. In meter is 0.020 power 4, and that will give you 0.3142 into 10 to the power minus 3 square meter. Now average normal stress in member BC will be equal to force BC divided by area of B area. All the areas are same. Similarly, average normal stress in member AC will be equal to FAC divided by area, and average normal stress in member AB will be equal to force in AB divided by area. So note down this value. FBC is this one, FBAB is this one, and the last FAC was this one. So you can put FBC, which was 50 kilonewtons, so 50 into 10 to the power 3 divided by area 0.3142 into 10 to the power minus 3, and that will give you 159 megapascal. Same FAC was 30 kilonewtons, so 30 into 10 to the power 3 divided by the area, which is 3142 into 10 to the power minus 3, and that will give you 95.5 megapascal. If you put the value of AB, which is 40 kilonewtons, so 40 into 10 to the power 3 divided by 0.3142 into 10 to the power 3, and that will give you 127 megapascal. So these are the average normal stress in BC, in AC, and AB of the truss members. And that was all about this problem 1-40. I hope you have enjoyed this video. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1-42. This problem is taken from chapter number 1, that is stress, and the book name is Mechanics of Material by R.C. Hibbeler. So statement is, determine the average shear stress developed in pin A of the truss. A horizontal force of P 40 kN is applied to joint C. Each pin has a diameter of 25 millimeter and is subjected to double shear. So you can see this is the truss. At point C we have a load of P, and at point A we have a pin support, and at point B we have a roller support. At A we have pin support. So you can see this is the side view, and there is a pin which is double shear. So we have to find the average shear stress developed in the pin. So let's start with the solution. So first step is that if you remove this support at point B, so you will be having a reaction force which is represented as By, and if you remove this pin support at point A, so you will be having a vertical force in downward direction which is Ay, and there will be a horizontal force in negative x direction which is Ax. So we'll find this Ay, Ax and By by using internal loading. So I will write internal loading. We will apply equation of equilibrium in order to find these stresses or forces. So first equation of equilibrium is that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, these two forces Ay and Ax are not producing moment because they are passing through it. So first moment that is produced by this By into perpendicular distance is 2 about point A will be in counterclockwise direction, so it will be positive. The second moment about point A is due to this P load, and perpendicular distance is 1.5 and it is producing clockwise, so it will be negative. And the sum of these two moments will be equal to 0 about point A. So I will write By into 2 minus P into 1.5 is equal to 0. So 2By minus P is given as 40. So 40 into 1.5 is equal to 0. So we will get 2By will be equal to 40 into 1.5. And when you calculate it, you will get By will be equal to 30 kilonewton. Now you have this By, so we will move and we will find Ax and Ay. So for finding Ax, we will apply this equation of equilibrium, that sum of all forces along horizontal must be equal to 0 and force in this direction is taken as positive. So you can see this force which is Ax is negative, plus this Py which is in this positive direction is P. So their sum must be equal to 0. So minus Ax plus P is equal to 0. So from here Ax will be equal to P, and we know that the value of P is 40 kilonewton, so Ax is equal to 40 kilonewton. Now you have this Ax as well, and we will find Ay by using in third equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So we have two forces, one is this one minus Ay and plus By, their sum must be equal to 0. So I will write minus Ay plus By is equal to 0. So Ay is equal to By, and By is equal to 30 kilonewton. Now you can see we have all these three reaction forces. So you can see that at point A, so if we find the reaction forces of these two, so this will be equal to A force, and this A force will be equal to, or we can also write Fa. So this Fa, by using Pythagoras theorem, net force at A, net force at A will be equal to FA, and that will be equal to AX square plus AY square under the root. So just put the value. AX is 40, so 40 square plus AY is 30, so 30 square. So from here when you calculate it, you will get FA will be equal to 50 kilonewton. Now this 50 kilonewton acts on this uh, pin support at point A. So you can see that we have been given that the pin is, each pin has a diameter of 25 millimeter and is subjected to double shear. It means that if you draw the pin like this, clear? So the net force that is acting on this pin is in this direction, or the direction of this will be in this direction. Why? Because two are both in negative direction. So this force will be equal to FA. So due to double shear, there will be a shear force VA in this direction as well as in this direction. So VA. So by using equation of equilibrium, that this shear force VA will be equal to F divided by FA divided by 2 due to symmetry. So 50 divided by 2 is equal to 25 kilonewton. Why? Because we have double shear. Okay, now you have this shear force, so we will move and we will find the average shear stress. So I will write average shear stress, which is equal to tau, and that is equal to shear force VA divided by shearing area. So how we will find shearing area? So diameter of pin is given, so shearing area will be this one, and this diameter is given 25 millimeter, which in meter is 0.025 meter. So area is of circular shape, or circular pin is pi by 4 d square. So put the value pi by 4 into 0.025 power 4 will give you 0.4909 into 10 raised to power minus 3 square meter. Now you have V, you have shear stress, so you can just put over here that average shearing stress is equal to VA divided by shearing area. Clear? So VA is 25 kilonewton. So 25 into 10 raised to power 3 Newton divided by shearing area is 0.4909 into 10 raised to power minus 3. And that will give you 50.9 into 10 raised to power 6 Pascal. And when you convert it into megapascal, so it will be 50.9 megapascal. And this is the answer of this question. So the average shear stress developed in pin at point A is 50.9 megapascal. And that was all about this problem 1-42. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.